Hello everyone, this is Dr. Kanthi Sudha, Assistant Professor from EC Department, VNR JYOTHI Institute of Engineering and Technology. So today we'll be discussing about coordinate systems and its significance in electromagnetic theory. So basically I come from a background of microwave engineering. So I have been dealing with these subjects of electromagnetic theory, antennas and wave propagation and microwave engineering, all which come under the category of the basis for electromagnetic theory as well as the application point of view. So let us see what is the flow of presentation which I would be discussing in this presentation. So one would be the introduction to the coordinate systems, then I will be discussing about the other coordinate systems, that is rectangular coordinate system, cylindrical coordinate system and spherical coordinate system. So let us go ahead on knowing what is the significance of related to coordinate systems. So why these are important for us basically in electromagnetic theory. So the choice of coordinate systems is always a strategic decision which we have to use for solving any kind of problems in electromagnetic theory, and some of them happen to be relevant to many kinds of applications like antennas, radiation, radar cross sections or transmission lines, waveguides. So there are many applications which we'll be discussing towards the end of this particular presentation also. So basically coordinate systems are used to specify a particular position of a point. So it can be like any point in space which you want to showcase using a particular reference frames, and which are nothing but your coordinate systems. So in the coordinate systems, basically depending on what is the problem statement, I mean what kind of application we are looking into, so we prefer to use that particular coordinate system which is relevant or apt to that particular application. So before we go into how we can apply and all this, let us first of all know what are these basic coordinate systems that we are looking into and why these carry significance in the concepts of electromagnetic theory. So if you take for example Earth is also one particular spherical surface where any kind of particular position, like for example if you are looking for a GPS coordinates, so you always look for a latitude and longitude. Now latitude and longitude are nothing but our reference points to tell us exactly where we are with respect to our position on the Earth. So just similar to that kind of thing, we can think about the coordinate systems also in space, where we are using Cartesian or cylindrical or spherical coordinate systems in order to understand the position of a particular point, either with respect to sources or either with respect to radiation or either with respect to the components whatever we are discussing in electromagnetic theory. Now let us go with the simple thing first, and which is the rectangular coordinate system. So already we are all aware of rectangular coordinate system on various occasions. I mean most of us might have been using this rectangular coordinate system where we used to talk about x-axis, y-axis, and in addition to that we are bringing in a third dimension, that is a z-axis also in this. So any position, for example in this particular slide you can see P is a particular point which is notified or which is notated with x, y, z. So which means to say what is the particular position of that particular point P with respect to x-axis or y-axis or z-axis. Similarly, we talk about planes also. When we talk about planes, we talk about xy plane, yz plane or xz plane. So these planes are basically with reference to the point where we are talking about whether it's an x is equal to 0 plane or x z equal to 0 plane or y is equal to 0 plane. So what do we mean by this? Basically YZ plane. YZ plane is where we are telling that x is basically 0. That means any particular component, if you are talking it's in a YZ plane, it's an implied thing that x is equal to 0. Similarly, when you talk about XY plane, we are trying to imply that the Z component is equal to 0. And similarly, when you are talking about XZ plane, we are talking about y is equal to 0 plane. So these planes carry a significance because whenever we are talking about any particular kind of a problem in electromagnetic theory, so these planes are going to give us an insight into where the particular position of a particular point is there. So this gives us a lot of insights into the position with respect to these x, y and z axis. So basically there are three axes in rectangular coordinate system. So if you look at the projection of the planes also, you can look at this particular figure where we are showing the constant coordinate surfaces. So we are talking about the three different colors of planes which are being represented here for an easy understanding of the constant planes. Like for example, orange is x is equal to constant plane, and blue is your z equal to constant plane, and green is y is equal to constant plane. So these are the constant planes which we are talking about. So any point on these planes, it implies that these values are going to be constant. So example for this is a rectangular coordinate system where p is equal to 1, 2, 3. It's being represented here, and similarly q 2 comma minus 2 comma 1. So these are the 2 points which we are representing at 2 different points with reference to these axes. So if I have to find the orthogonal vector related to this will be nothing but x plus y plus z. And coming to the unit vectors are nothing but which give an indication of the direction sense. Okay, so if unit vectors basically have a magnitude of unity, so they are only used for indicating the direction related to these coordinate systems. So for example, we represent the unit vectors in coordinate systems, especially Cartesian coordinate systems, with ax, ay and az, which will be the unit vectors along x, y and z directions. So coming to the vector representation, now suppose I want to find out the distance between 2 points. For example, the 2 points which we have taken in the example, that is p of 1 comma 2 comma 3 and q of 2 comma minus 2 comma 1. So how can we find out the distance between them? So this can be done in two ways. One is either you find the position vector with respect to point p, you find the position vector with respect to q, that is rp and rq. So position vector is nothing but the distance from your origin to that particular point under consideration. So once you find the position vectors, so the actual distance between these 2 points is nothing but the difference between these 2 position vectors. For example, if I am finding the distance between p and q, that is which is represented with rpq, so the position vectors rq and rp, so if you consider them individually, find the values and then you subtract one from the other, that is when you get your total distance between these 2 points. It's as simple as that. Similarly, when you talk about differential volume, so when you talk in Cartesian coordinate systems, the three-dimensional figure which comes into consideration for us here is a cuboid. Is a cube. So in a cube, basically you have all the 3 dimensions, that is dx, dy and dz. So dx is called as your differential displacement. So generally when we notate with the distance dx, which is differential displacement along the x-axis, dy along the y-axis and dz along the z-axis. Now when we are talking about the volume, so we take the particular individual face of the cube in order to find the differential area if you are talking about. So like for example, if you are taking the top face or the side face, something like that, so then you can take dx dy or dy dz or dx dz, so like that. So the differential area will be nothing but the product of these 2 things. And the unit vector which comes out of this differential surface area, that is going to be the direction in which your component is going to be there. For example, if I take the surface like the top surface, here in this case dx dy is the 2 sides which we have on the top face, and az is going to be the unit vector which is going to point out to the resultant vector which is going to be in that particular direction. So differential volume element can be found out in Cartesian coordinate systems by taking a cube into consideration. So these are the different expressions related to differential displacement, differential normal area or differential volume considering the components dx, dy and dz. So if I am talking about differential displacement, the maximum differential displacement that is possible from one corner of the cube to the other corner is basically dx ax, dy ay plus dz az. So that is why how you are covering all the 3 dimensions when you are looking from one diagonal corner to the other diagonal corner in a cube. So similarly, the differential normal area also, as I told you, you can take any particular face and you can calculate what is the differential area corresponding to that associated with the unit vector which indicates the direction of the resultant. So differential volume is basically dx, dy and dz also. So coming to the cylindrical coordinate system, now this is something which probably you might not have come across previously. So there are 3 coordinates which are used in the cylindrical coordinate system. One which we call it as rho, which is a circular cylinder. If you take rho is considered to be the radius of the cylinder. Then you have phi, which is the the azimuth angle, which is constant and then you have the z. So z axis is just like your Cartesian coordinates where you have talking about z. So here also we have a z component. So the rho, phi and z, so these are the coordinates which are being used in a cylindrical coordinate system. So basically depending on how you are using the coordinate system, so it depends on which components you can bring it into picture. Now for example, look at this particular figure. So when we are talking about rho is a radius. So the what do you call, the limits of rho always have to be positive. That means you can't have a negative radius as such. So that's why the units, the limits of rho will be always from 0 to infinity. Similarly, when you take phi is the azimuth angle where the limits can be from 0 to 2 pi, and z is something which is the height of the cylinder. So height of the cylinder, you can have a negative value provided the placement or the position of your cylinder. Like for example, your cylinder can be above the z axis, above the z equal to 0 plane, and above below the z equal to 0 plane also, depending on which you can have both positive as well as negative values, which is possible in cylindrical coordinate system. So if you come to the particular planes of the constant coordinate surfaces in cylindrical coordinate system. So again, based on these three coordinates, whatever we are talking about, so rho, phi and z. So they are the constant planes associated with these coordinates also. So rho is equal to constant is nothing but the radius of the cylinder. So yellow colored one which is being shown here. So this is basically rho is equal to constant plane. Z equal to constant plane is something where you are taking z is equal to it's going to be a constant value there, and then phi is equal to constant is the blue colored one, which is indicating how phi is equal to a constant value plane can be. So coming to the representation of the vector for this particular cylindrical coordinate system, you can always represent it as a rho and a phi and a z, the combination of these three vectors, and the magnitude of the resultant vector will be the under root of square of these three terms. So in this scenario, if you look at the particular point, or in this example, if you look at the particular point P, so it is 3, 45, 8. So here rho equal to 3. That means the radius of the cylinder is 3. 45 is the angle pertaining to phi. So that's why you have written 45 over there. And 8 is nothing but the height of the cylinder, that is z equal to 8. So coming to the differential area or differential volume. So to understand this particular thing, so we are taking here a particular cross section of a cylinder, a small cross section of a cylinder, where we want to indicate what is d rho, what is d phi and what is dz. So here if you see dA, so this particular dA is basically what you call the d rho, because it's a small portion of the rho which has been extended. Then dz is nothing but the small portion of the height, that is from A to B. And similarly, when you talk about this one, this is basically BQ, or you can say BQ is basically the arc radius, because it's a curved surface. Cylinder is always a curved surface. So when you talk about BQ is basically the curved surface which is subtending an angle of d phi, because d phi is the small angle which is there for this particular cross section sample which we have taken. So this is going to be d phi. So when you say this is d phi, so this is d phi. So when you say this is d phi, so obviously this is rho, the radius. So when you talk about arc length, L equal to r theta is the formula which we have. So when you say L equal to r theta, so then obviously the arc length is basically going to be L equal to r theta. So r is radius and theta is the angle that is being subtended at the center. So now here in this case, rho is the radius and d phi is the angle which we are talking about. So obviously this particular what you call length is going to be what you call L into rho into d phi. So that's why it's called the arc radius, which is being represented with this particular terms. And similarly, if you see the unit vectors, they are also been notated with a rho, a phi and z, az, basically indicating the directions in which these coordinates are there. So if you can better have a better view of this particular cross section whatever we are discussing, so this is how it is. So the angle phi and the cross section whatever we have taken, so it is basically a small angle deviation, that is d phi, and similarly rho also, if there is a small deviation, that is d rho, and similarly when there is a small deviation with respect to dz also. So that is how we are talking about d rho or d phi or dz, the small differential displacement with respect to the three different coordinates. Now when you come to the differential volume, dv is going to be rho, d phi and dz. So this differential volume is basically understood more clearly when you look at the particular cross-section sample that we have considered previously. So in this also, what we are considering is we are looking at the three different phases, because in any particular sample, if you take, the sample has got symmetry basically. So any two phases will have the same symmetry. So obviously, though it has 6 phases, there is 3 phases which we can consider, because obviously the other three are going to be symmetrical with respect to these 3. So when you consider this, we are just looking at the lengths across the surfaces, which surface has got which length along which direction, and also the unit vector which is coming perpendicular out of it or orthogonal to it. So that is how you can get the differential area or the differential volume here. Now in this case, if you see, for example, if you take the side face, you have d rho and dz as the two what you call the lengths along this particular surface, and a phi is the unit vector. So when you write the area, it will be like d rho, dz and a phi. So always remember that whatever you are writing the differential area, the unit vector is very mandatory, because that is the one which indicates where is the resultant basically. If you look for the differential displacement of a cylinder, this is how it is: dl equal to d rho, a rho, rho d phi, a phi, dz, az. And differential normal area, which is given by these expressions, and differential volume corresponding to this. So then coming to your spherical coordinate system. So spherical coordinate system again has got 3 coordinates, r, theta and phi. So r is basically the radius of the sphere, because in spherical coordinate system, sphere is the geometrical structure which we are considering here. So radius of the sphere happens to be one of the coordinate, and theta is your elevation angle, which here is going to become one of the coordinates in spherical coordinate system, and phi basically is your azimuth angle, which is again going to be one of the coordinates. So the constant planes corresponding to these, and the unit vectors, same as cylindrical, here also we have. So coming to the constant coordinate surfaces for a spherical coordinate system. So this is the figure which is representing r equal to constant, theta equal to constant, and phi is equal to constant. And also correspondingly, what is the differential volume? Just like we have calculated for a cylinder, even for the spherical coordinate system also, we can calculate the differential surface area as well as differential volume corresponding to that. So here also we'll be taking a small sample of it, and the corresponding sides are going to be found out individually corresponding to the 3 different faces, which will have symmetry with the other 3. So based on what you are going to get over there, the values of the lengths of these sides, and basically the unit vector which is going to be normal to this particular surface. Apart from all these 3 coordinate systems which are used for various applications and various problem solving things, so we also have the provision for coordinates transformation. That means if you have one coordinate system, you can obviously calculate the other coordinate system by having a relation between them. So like for example, there is a relation between cylindrical and Cartesian. So you can always do a transformation from cylindrical to Cartesian and Cartesian to cylindrical also. And same goes with the spherical coordinate system also, where we have a provision for transformation of coordinates from one particular system to another particular system. So here we can take the transformation required based on the problem statement. For example, if a problem is given in Cartesian, I mean, if you find that the analysis can be done in a Cartesian very easily, and then you can transform it into spherical also. Or same way, if you can work it out in spherical, and you can also come back to your Cartesian and all. So there is a flexibility of transformation from one particular coordinate system to another particular coordinate system, which is a very important feature in the Cartesian in the coordinate systems of electromagnetic theory. Now coming to the practical engineering applications of where we can use them, I am just giving 1 or 2 examples here so that you have a better understanding of how these coordinate systems will be helpful for us in various contexts. So for example, if I am talking about transmission lines, so I think cylindrical coordinate system can be useful. Even in antenna design, you can talk about spherical coordinate system, because we are talking about radiation, how the radiation is going to be there in free space. So all these things, I think they can be better analyzed if you go for a go with a spherical coordinate system. And if you are talking about a radar cross section, then often it's basically spherical coordinate system which will be taken into consideration. And in waveguides, probably you can go with either Cartesian or cylindrical also. So it depends on the applications basically. What kind of application are you looking at? What kind of structure are we looking at? What is your source? What is your radiation? Where is your point of analysis? So based on that, you can always take into consideration. As I told you, a choice of coordinate systems is going to be a very strategic choice in solving your EM theory problems. So that is why it's very important on how best you choose the coordinate system. So thank you, and hope if you have any doubts, you can leave it as a comments in this video. Thank you.
Like, share, comment, and subscribe VNR Digital Learning Resource YouTube channel.